Okay, so we start 2 days with the air matrix, 2 long days with the lectures in the morning and exercises in the afternoon. So I will show you that the air matrix is an important tool not only for experimentalists but also for theoreticians. That there are two aspects of the air matrix. One is to solve the Schrödinger equation. This is essentially targeted to theoreticians. And the other aspect of the air matrix is to fit data, and this will be essentially discussed by Ed in his lectures and exercises. But in fact, as I'm going to show you today, the origins of these two aspects is common, and in fact there is a single origin of the air matrix, and at some point you can divide it in two directions according you want to solve the Schrödinger equation, and this is called the calculable air matrix, or if you want to fit data, and this is called the phenomenological air matrix. So I will briefly introduce the air matrix, what is it used for, and then also a brief introduction to scattering theory. I think you have heard a lot about scattering theory in the last 2 weeks, but this is important to specify my notation and maybe to refresh your memory with the important aspect of the scattering theory. And then I will introduce today the general air matrix formalism, so the very beginning of the air matrix. And then today I will show you applications of the calculable air matrix. So this is in the situation where you want to solve the Schrödinger equation by using the air matrix. And I will show you two examples. One is more a textbook example. It's potential model. Of course, you can solve the potential model by several methods with a Numerov algorithm. It's very simple. So it's a nice case to understand the air matrix, to make simple calculations. And in fact, the exercise session of this afternoon will be about the potential model with the air matrix. And then I will show you a more practical and more recent application to CDCC calculations. You have heard about CDCC, and probably you have done calculations by yourself. And I will show you that the air matrix is also something very efficient to solve the CDCC equation. So the first question you may ask yourself is, why the air matrix, and what is it for? And well, the main answer is that you want to treat the long-range behavior of the wave function. So imagine that you have a situation like this, where the important things occur in a limited region. So in that case, you may divide the space in two regions. So you have the internal region where the physics of the problem is important. And here, the external region where almost nothing happens. So if you are happy with the internal region only, then you don't need the air matrix. But if for some reason you believe that the external region should be corrected in some ways, like you have for scattering states here, or even if you want to pay attention to the exponential decrease of a bound state, then you can use the air matrix. Okay, so more seriously, the air matrix. So in the air matrix, you know that in scattering theory you start from cross sections, which can be either measured or calculated. And these cross sections you have seen many times in different lectures. These cross sections are at least at low energies computed from the phase shift, or more generally the collision matrix or the scattering matrix. And this phase shift can be obtained either from phenomenological theories like the air matrix, or from some theories. And you have here various theories like microscopic models. I will talk about microscopic models on Wednesday. CDCC, you have heard about that. The optical potential, optical model potential, and probably other methods. And here in all these methods, you need something to compute the scattering matrix. And one possible tool is the air matrix here. And these are the two variants, the phenomenological and the calculable air matrix. So this air matrix was in fact introduced a long time ago by Wigner in 1946. And at that time, the main goal was to describe resonant data. And in fact, now we know that this is not limited to resonances. You can describe also continuum processes with the air matrix. And from the very beginning, the idea of the air matrix was to divide the space into regions according to whether the nuclear interaction is important or not. So in the internal region, the nuclear interaction is supposed to be dominant. So you have a combination of nuclear and Coulomb interactions. And here, so you don't know the analytical form of the wave function. So here in the internal region, you expand the wave function over a basis. And this basis should not be specified from the very beginning. It can be Gaussian functions, Legendre polynomials, or whatever. And in the external region, by definition of the channel radius A, the nuclear part is negligible. So you are left with the Coulomb interaction, and then you know the exact analytical form of the wave function, just a combination of Coulomb functions. And in fact, there are many applications in atomic physics. Most of the developments of the air matrix have been done in atomic physics. There are also applications, of course, in nuclear physics. And for a long time, the main references was this Lane and Thomas in Reviews of Modern Physics, 1958. It's a very big paper which contains almost everything you want to know about the air matrix. But this is, well, if you know about the air matrix, it's very fine. But if you don't know, then it may be hard to read. So we wrote with Daniel Bay reports on progress in physics with a more modern presentation. I will show you what is more modern, and also with several examples, simple examples, that's how we are going to do this afternoon, that you can easily repeat yourself to understand the air matrix. So as I said, there are two directions of the air matrix with a common origin. The calculable air matrix, where you extend variational calculation to scattering problems, and the phenomenological variant, where you want to parameterize the cross-section. So this is shown here also, the two situations. One is for theory, you want to solve the Schrödinger equation with positive energies, and the other situation is represented here, a typical situation. You have a cross-section. Here it's, I think it's near 19p elastic scattering. And you see that there are structures, resonance here, and you would like to know about the properties of these resonances, the spin, the energy, the width, and so on. And so in both cases, the possible tool is the air matrix. Okay, so in the calculable air matrix, we know that in many problems in physics, you end up with a coupled channel problem. So you have seen this equation many times in the previous lectures, for example, in CDCC. And well, this is very general, so it can be adapted to nuclear physics or to atomic physics. The only limitation is that it's non-relativistic. It's in the Hamiltonian, in the Schrödinger picture, where you neglect all relativistic effects. So you have here a set of coupled equations. C here is an index for the channels. You have the energy of the process, energy of each channel, and a coupling potential. And so here, this equation is common to many problems, and the only difference is VCC, the coupling potentials. So if you are interested in bound states, and bound states mean that the energy of the system here is lower than all threshold energies, so you have a bound state, it cannot break up, then you can use variational methods. So these are very well known in physics. But if you have positive energies, so either you have scattering states, so you want to study the collision between two particles, or if you are interested in resonances, then it's more difficult, and then you need something more than variational methods. And I show you here one example, few examples of the CDCC, and I will come back there on my application at the end of the talk. So you have heard about that. You have a two-body projectile, or three-body, but essentially two-body projectile with particles 1 and 2. And then you first solve the two-body problem. So you first solve the Schrödinger equation associated with the projectile, and you get these two-body wave functions. Then what you want to determine are these relative wave functions, so that they define the motion between the target and the projectile. And then you end up with a coupled channel system. Another possible application is microscopic cluster models. Here the model is different. All nucleons are included in the wave functions. So I will talk about that on Wednesday. And I will not talk about that, but I'd just like to mention that you may be interested in three-body continuum states. This is important in some exotic nuclei, for example, helium-6, lithium-11. The breakup threshold is very low, so very soon you are in a continuum, and then you need three-body continuum states. And again, you have this kind of equation. And the limitations here are, well, you know that the potential the nuclear potential should be negligible. So in some case, you may have a long range of the potential, and this means that you will need many basis states. I will show you examples. At high energies, you also may have problems because you need many partial waves, and you know that high energy means that the wave function oscillates very fast. So you need a basis to describe this fast variation of the wave function. And another limitation comes from the number of channels. So the number of indexes here, J, L, N, may be sometimes several hundreds. So you have a system with many coupled channel equations, and this is a numerical challenge. Okay, so you have heard about alternative method, which is a discretization method. So if you don't want to use the R matrix, you can use the Numerov algorithm, and this is used by Fresco that you have used before. And so sometimes I'm asked, what's the best method? Is it the Numerov algorithm or the R matrix method? And to be honest, I don't have an answer to this question. But I think this is an interesting question, because you can optimize the R matrix and the Numerov algorithm. So it would be nice to have some comparison with in optimal conditions. But at least these are two equivalent methods. So whatever the one you prefer, you can use both and check one with the others. So they should provide the same results. And well, an obvious advantage of the R matrix concerns the closed channels. This is difficult with the Numerov algorithm. So imagine that you have a situation like this. You have 4 channels, and you are at a collision energy, scattering energy, which is between these channel 3 and channel 4. So the physics of the problem doesn't matter here. The point is that you are between channel 3 and channel 4. So here it means that channel 1, 2, 3 are open. So at large distances, well, sorry, this is not a very nice plot, but this is supposed to be a sine function, something like a sine function. So there are oscillations. But channel 4 is closed at these energies. So you know that at large distances, you will not have such an oscillating behavior, but you will have something which decreases exponentially. And this is a numerical problem, because the solution of the Schrödinger equation are a combination of a decreasing exponential and of an increasing exponential. And so you always have a slight, in a numerical point of view, a very small amount of this increasing exponential, and this is a big problem in numerical procedure with the discretization method. In the R matrix, you don't have this kind of problem. Closed channels are easily treated. So this was for the calculable R matrix. So in the phenomenological R matrix, the R matrix, which here it's written for one channel, which is a function, the R matrix is an intermediate calculation before getting the scattering matrix. And in the phenomenological R matrix, the R matrix is written like this, where you see the energy. This is a scattering energy. And here you have two parameters. One is the energy, and the other one is the reduced width of the resonances. So these parameters can be fitted to the data, and then you get the phase shift and the cross-section. And I've listed here some examples. Well, for example, resonance properties from elastic scattering. So there are several examples. In nuclear astrophysics, also the R matrix is a very convenient tool, because in most cases you have data at high energies where the cross-section can be measured, and you are interested at very low energies where you cannot measure the cross-section. So the R matrix is then used to extrapolate available data to low energies. And I've shown here a third example. In fact, there are other examples. Beta decay to unbound states. So for example, boron 8, which decays to 2 alpha. So in general, the R matrix is a very useful tool where you have to deal with the continuum. So as soon as you have continuum states, as in all these cases, the R matrix is something very useful. And of course, in this variant, the phenomenological variant, there are also limitations. One is the level density, because each level is associated with a set of parameters here. So if you have many levels, 10, 20 or more levels, then you are left with many parameters. And then this is the problem to find the optimal set of parameters. Another problem is associated with the number of open channels. So this simple expression for the R matrix assumes a single channel. But of course, when you have many channels, it gets more and more complicated. You have more and more parameters. So from these two requirements, you easily see that the R matrix is well adapted to light nuclei, because in light nuclei, the level density is in general rather low, and at low energies, because also the number of open channels is low and the level density is low. So before going to the R matrix, I spend 5 minutes to refresh your memory with scattering theory. So probably you have heard about that last week and the week before. So the scattering theory tries to solve the Schrödinger equation, which is written here in a very general form, the Schrödinger equation with positive energies. That's the main point. And here I make some simplifying assumptions just to simplify the presentation. So I assume that there is no internal structure of the colliding nuclei. So there are 2 points, and they interact by a potential V. So I limit myself to elastic scattering with a single channel, and I neglect the spin. So these are the main approximations. And then, as you know, you have a wave function with index Lm, which can be factorized in a radial part and a angular part, which is a spherical harmonics, and then you derive the radial part by the standard Schrödinger equation. So at large distances, the nuclear potential is negligible, and then you know the analytical solutions of the Schrödinger equations, which are Coulomb functions, f and g. This is the regular and irregular Coulomb functions. There are Fortran subroutines to determine these functions. And from there, you define the incoming and outgoing functions by a combination of g and f. And I, the incoming functions, are this asymptotic behavior. So it's a wave which enters the nucleus. The otherwise is outgoing waves. And then from these Coulomb functions, you define an important quantity for the R matrix. These are called the shift S and penetration factor, which is simply related to which are simply related to the logarithmic derivative of function O at radius A. I told you last time the notation S is used in many cases in nuclear physics, and here again is completely different from spectroscopic factor or from the astrophysical S factor. And these are important quantities for the R matrix, and you have here an example with for the penetration factor and the shift factor. This is done for alpha plus helium-3, where the Coulomb barrier is at about 1 MeV. So this is a penetration factor plotted as a function of energy, and for triangular momenta, 0, 2, 4. And as you can see, there is a strong Coulomb effect below the Coulomb barrier. This is related to the fact that you are far below the Coulomb barrier, so the probability, the penetration probability is quite small. You can see here you have a logarithmic scale, and you also see that when you increase the centrifugal barrier for a given energy, this probability vastly decreases. And on the right-hand side, you have the shift factor. And here it's a very smooth function of energy. You have here a linear scale. And you have these are the same energies, but you have the linear scale here. And in the R matrix, one often uses what is called the Thomas approximation. And the Thomas approximation is just to assume that the shift factor is linear, at least linear in a limited range. So I will come back to that later. So the wave function at large distances tends to a combination of incoming and outgoing functions, with U is called collision matrix or scattering matrix. And U can be written as exponential to I delta, where delta is the phase shift. So this is true for single channel calculations. And this delta is real if the potential is real, and then when you compute it for each L, then you can determine the elastic cross-section. So probably this is something you have seen last week. So you just compute the scattering amplitude, F, from this expansion over L, where you have here the phase shift and here the Legendre polynomial. One of the problems which is associated with this expansion is that it converges very slowly due to the Coulomb potential. So if you use this formula with the Coulomb phase shift, you will see that you need thousands of partial waves. And this is not very convenient. So what is done is to split this amplitude in a Coulomb and in nuclear part. So you just add and subtract the Coulomb part. The Coulomb part is known analytically, and the nuclear part is written like this, where you have here only the nuclear part of the phase shift. And this is a function which converges very rapidly. So you have two parts in the scattering amplitude. One is the Coulomb part, which is exact, analytically exact, and another one which is to be computed numerically but converges very fast. And the Coulomb part provides you with the Rutherford cross-section. It's shown here as a function of theta, 1 over sine to the power 4 of theta half. And well, at small angles, as we know, the Coulomb part diverges. So at small angles, Coulomb is always larger than the nuclear part, and this is used to normalize data. Because when you are very small angles, you know that the cross-section is Coulomb, and you know it analytically. And this Coulomb part is minimum at 180 degrees, and so this is where you expect the nuclear effect to be maximum. So, well, as this cross-section strongly depends on the angle, usually one provides a plot of the elastic cross-section divided by the Rutherford. And this is an example with the lithium-6 plus nickel system. And you see that when you increase the energy, you see that there is a departure from the Coulomb behavior, which is more and more important. Here it's low, very low energy, so the ratio is 1. So it means that it's essentially Coulomb. And when you increase the energies, you have departure from 1. So one of the simplifying assumptions was that it's a single channel calculation with 0 spin nuclei. And if you want to extend that to multi-channel calculations, then the scattering matrix U, which in fact is a single number, in single channel calculation it's a number, is extended to a matrix with index I and J, which corresponds to the different channels. And then the scattering amplitude should also be generalized, and then the cross-section can be defined not only for the elastic process, but also for inelastic process and transfer process and so on. And one of the nice things for inelastic channels is that the cross-section only contains the nuclear part. So there is no Coulomb effects when you are looking at inelastic, not direct Coulomb effect in elastic or transfer cross-sections. So this collision matrix or scattering matrix is symmetric and unitary. And now the good quantum numbers which are associated with the system are the total spin and the total parity. So the situation is shown here. So you have two nuclei with spin and parity I1, pi1, I2, pi2, and a relative angular momentum L. And the good quantum number is the total spin, and the total spin is the coupling of I and L. I is called the channel spin, so you first couple I1, I2, and then L to get J. And you have the standard selection rules here, which comes from angular momentum coupling. And you have some example here with alpha plus helium-3. We know that the spin of the alpha is 0 plus. Spin of helium-3 is 1/2 plus. So here you have the different J values. The channel spin is the coupling of 0 and 1/2, so it's always 1/2. So now if you look at the possible L values, if you couple these two, you can get 0 or 1. And in each case, the same, 0 or 1, 1 and 2. But then the parity selection rules tells you that here, because we have parity plus, then L must be even. So L equal 1 is forbidden. Here L equals 0 is forbidden, and so on. So in all cases here, you have a scattering matrix which has a size 1 by 1. Now if you have a slightly more complicated example with proton beryllium-7, beryllium-7 is 3/2 minus, proton is 1/2 plus. So the channel spin is always 1 or 2, the coupling of this 3/2 and 1/2. So here you have the possible L values, but here again the parity provides an additional selection rule. So you see here you have a negative parity. So to have 0 plus, you need L equal 1. So it means that this channel is forbidden. And for 0 plus, you have size 1. For 0 minus, the same thing. You have size 1. For 1 plus, then here you have several L values. But for 1 plus, again, you need odd partial waves. So these three are forbidden, and you end up with a scattering matrix which is 3 by 3. So the size of the scattering matrix depends on the J values. And then in a multi-channel calculation, the one-channel cross-section is generalized to a multi-channel definition. So you have an additional indexes here to the scattering amplitude, and this K1, K2, K'1, K'2 corresponds to the spins orientations in the entrance and exit channels. And what I don't want to enter into details here. This is you can find in many textbooks or review papers. But the important thing is that in this scattering amplitude, you have the collision matrix, which is a generalization of the phase shift. So this is exactly the same calculations are in the single channel problem. It's just a little bit more complicated because you have more indexes. So let me start now with the general presentation of the R matrix. So again, I assume that there are two structureless particles and only one channel. And I will show you that the R matrix is an extension of the variational method. Variational method is very well known in physics. You have an Hamiltonian, and you are interested in bound states, so negative energy states of this Hamiltonian. And in a variational method, you start from a basis, for example, Gaussians or others, a basis, so a set of n basis functions, and you expand your wave function over this basis. And then from matrix element of the Hamiltonian, you can get an approximation of the binding energy. But there is a problem for scattering states, because these basis functions phi should tend to 0 at large distances. Because you must be able to define integrals with this function phi. So if you take a finite combination of these functions, so Ci here are coefficients, this is a finite combination of functions, and if finite combination will tend to 0. So you cannot describe a scattering state because we know that the scattering state oscillates at large distances. So this is why the variational method must be complemented by something, and this something is the R matrix. So the idea is to divide the space, so here is the coordinate R, the relative coordinate, in two regions. And there is the channel radius A, which makes the difference between the internal and the external regions. So this channel radius is chosen large enough so that the nuclear part is negligible here. So in the external region, by definition of this A, the external contribution to the wave function is a combination of the Coulomb functions. So we know that from the very beginning. And in the internal region, we don't know the wave function, so we use the internal definition as an expansion over the basis. So now this basis is not used until infinity. It's used only in the internal part. And beyond this internal part, you have an exact Coulomb waves. So from the matching of this internal and external part at A, you can get the phase shift. And here, I'd like to mention some important thing is that the channel radius is not a parameter. It's just some tool to determine, intermediate tool to determine the scattering matrix. So at the end, the physical properties, so which is the wave function here or the scattering matrix, should not depend on this channel radius. So this is a very strong test of the calculation, and I will show you some example. So, so the first step in the R matrix is very similar to variational calculation. You know, in variational calculation, you have an Hamiltonian, you have a set of basis functions, and you compute the matrix element from 0 to infinity. But here, because the basis functions are valid only in the internal region, you compute this matrix element not from 0 to infinity, but from 0 to A. So this is the idea of the R matrix. So you compute this internal matrix element from 0 to A. This is for the Hamiltonian, and this is for the overlap. And you can see from that there is a problem with the kinetic energy. And the problem is that the kinetic energy is not Hermitian if the range is finite. Because if you take matrix element of the second derivative here, it's not symmetric. There is a term coming from, these are well-known analytical properties, so you cannot exchange here I and j if the upper limit is finite. And this is the reason why there is this Bloch operator. So Claude Bloch was a French physicist, and you know that there is here a street and a bus stop which are called Claude Bloch. And he was someone famous, but he died very young. I think he was 30 years old or something. But this is the one who introduced this Bloch operator. And you can see that in this Bloch operator, there is a delta here. So the Bloch operator is also called a surface operator. It only acts at the channel radius because of this delta. And there is a constant here, L, which can be chosen arbitrarily. And in most cases, we choose it as 0. So the role of the Bloch operator is that when you add it to the kinetic energy, then the sum of these two operators is Hermitian. So this Bloch operator introduces what is missing to the kinetic energy to make it Hermitian. So when this Bloch operator is introduced, the Schrödinger equation becomes Hermitian. So the idea is to replace the standard Schrödinger equation, which is written here, by the Bloch Schrödinger equation. So you just add one term on the left side and on the right-hand side of the Schrödinger equation. So you have, you add here L on the left-hand side and L on the right-hand side. And this is valid for the internal function. But you know that at the surface, at R equal to A, the wave function is continuous. So here you can replace the internal function by the external function. And so you can see that this Bloch Schrödinger equation is equivalent to two equations, because there is a term which contains the delta function and a term which does not depend on the delta function. So you have to make these two terms equal, and if you do that, you see that this Bloch Schrödinger equation is equivalent to the standard Schrödinger equation. This is the term which does not depend on delta. And if you look at the term depending on delta, then the Bloch operator guarantees that the derivative of the wave function will be continuous. And this is one strong advantage of the Bloch operator. And this was not in the old use of the R matrix. There were no Bloch operator, and then basis states were chosen in such a way that the derivative was always 0. And then you avoid this hermiticity problem, but then you are very limited to the basis function. So it means that your function, which will be a combination of this basis function, will always have a derivative 0. And this is a limitation of this old technique. Okay, so let me continue with this R matrix. So you start with 4 equations. So one is the Bloch Schrödinger equation. One is the expansion of the internal wave function. One is the definition of the external wave function. Another one is the continuity of the wave function. So now, if here you expand, you use this expansion, and you project on some basis function phi I, you end up with this system. So this is a very simple calculation. And then you see that here this is a matrix, so here everything is known. You know the Hamiltonian, you know the basis function, so you can compute this matrix D. And so these are n equations. And well, when you invert that, you can easily find the coefficient Ci. And then you use the continuity equation here. So you have here an additional equation. So you have n unknown quantities, the Ci here. You have one unknown quantity, which is the scattering matrix. And so you have n plus 1 unknown quantities, and you have n plus 1 equations. So everything is well defined. And well, when you use this continuity equation here, then you end up with the scattering matrix U, which is here, and which is expressed as a function of the R matrix. So you can recognize here the inverse of the matrix D. So this is what you need to get coefficient Ci. So this is a very simple calculation. And this R matrix is 1 by 1 for single channel calculation. And L, which appears here, is the Coulomb function that I have mentioned before. So you have your basis function, so you determine matrix D, then the matrix R, and then the scattering matrix. So these calculations are rather simple. This is presented here for single channel calculations, but it can be easily extended to multi-channel calculations. Okay, so you have seen this scattering matrix can be factorized. You have here a term which is I over O. So this I and O are complex conjugates. So this has modulus 1. And this is called the Hart-Sphere phase shift. So it is defined by I over O is exponential 2I delta Hart-Sphere. And if you use the definition of I and O, then you can easily find this Hart-Sphere phase shift. And the other contribution comes from this part. And as you can see, these are also two complex conjugate numbers because the R matrix is real if the potential is real. So the modulus of this term is 1, as you expect for a scattering matrix. And this provides you with the R matrix phase shift. So this is this term. And if you replace L by S plus IP, then you get this expression. And you can easily determine the R matrix phase shift. So here R is the R matrix, and P and S are Coulomb functions, penetration factor and shift factors. So it's rather simple calculations. And so you can see that the total phase shift is the sum of the Hart-Sphere and of the R matrix phase shift. And both of them depend on the channel radius because explicitly you have the channel radius here, you have the channel radius there, but the sum should not depend. And this is repeating the calculation for different channel radii is a very strong test of the calculation. So if you have real potentials, then R, the R matrix is real, delta is real, and the square modulus of U is 1. And if you have a complex potential, which is supposed to simulate absorption, then R and delta are complex, and the modulus of the scattering matrix is lower than 1. Here you have pictures for the Hart-Sphere phase shift. Again, it's for alpha plus helium-3. You have here the energies in MeV, and here the scattering, the Hart-Sphere phase shift in radians. So you can see that there is here L equals 0, Hart-Sphere phase shift, which is rather important. And when you increase L, this Hart-Sphere phase shift is smaller and smaller, and again this is due to the centrifugal barrier. So here are the properties of the Coulomb function. You have here again the same penetration and shift factor, which are very important to compute the air matrix phase shift. So this is a general theory. The calculations are very simple. You can do that in a sheet of paper very simply. And now I'd like to show you two applications. One which is very simple, which is the potential model. And there you know the exact solution, so you can easily test and compare with reference calculations. And the other one is CDCC calculation. So here I'd like to solve this Schrödinger equations, single channel Schrödinger equation, for the alpha plus alpha system. And for the alpha plus alpha system, we know that there is a very good potential by Buck. And here there is a typo, it should be to the power 2, it's to the square. So this is a Gaussian potential, and we know that it reproduces very well the alpha plus alpha phase shift. So the goal here will be to compare the exact solution with air matrix calculations in different conditions and see how sensitive are the phase shift when you change the conditions. So here the basis functions are taken as Gaussians, and you see here the width of the Gaussians are in a geometric progression. So you have, they are shown here. So the different basis functions correspond to Gaussians with wider and wider width. So this is the set of the basis functions, and this is the potential. So you see that here you have in pink the Coulomb potential. So this is the alpha plus alpha distance, this is the potential. The blue curve is the nuclear potential, which corresponds to this Gaussian, and the yellow curve is the sum. And this is important to decide about the choice of the channel radius, because you have to make sure that the nuclear interaction is negligible. So here you can see that, let's say, from 6 Fermi, the nuclear interaction is negligible. So you have to choose your channel radius in this region. If you choose it here, then you are not in the conditions of the air matrix. Okay? So this is the experimental situation. You have here the experimental spectrum of beryllium-8. We know that beryllium-8 is unstable, so the ground state is unstable with respect to alpha decay. So the energy is very small, 0.09, and the width is also very small, 6 electron volt. And you have here the experimental phase shift. So you see here the phase shift for L equals 0. It starts from 180 degrees, which corresponds to this very narrow resonance, but the width is very small, so it cannot be observed experimentally. 6 electron volt is much smaller than the energy resolution that you can expect. This 2 plus broad resonance can be seen here in this pink phase shift. You have resonance here around 3 MeV, which correspond to these states, and here a broad 4 plus resonance, which correspond to here. So there is a correspondence between the phase shift and the level scheme, as it should be. Okay, and again, this is here the potential with the Coulomb barrier around 1 MeV. So the inputs are the potential I've shown before, the set of basis functions, which here are Gaussians, but you can use other functions if you like, and the channel radius. And we request that this channel radius should be large enough to make sure that the nuclear part is negligible. And of course, the number of basis functions should be also large enough, because you have to reproduce the internal part of the wave function. So if your number of functions is too small, as it can be in any variational calculation, then you will get in trouble because you cannot reproduce the internal part. So n should be large enough to reproduce the internal wave functions. And of course, you want n to be as small as possible because of computer times. And in this application, you will see that all computer times are very short, so this is not really an issue. But in some cases, it can be very long, and then the choice of n is a really important issue. So there is a compromise in the choice of the channel radius. I will show you an example. So this is the procedure as I've shown before. So the first thing is to compute this matrix D, and this is an integral from 0 to A of this element. It can be generalized to any model. I will show you microscopic model. So the idea is to compute a matrix element in a limited space from 0 to A. And here we have a single dimension problem. So the coordinate is R. So we integrate here from 0 to A. So once we have this matrix D, we invert matrix D and we compute this R matrix and then the scattering matrix. And of course, you have tests. And as I said before, one of these tests is the stability of the phase shift when you change the channel radius. And another test is the continuity of the derivative. I've shown you in one of my first slides that with the block operator, you have the derivative continuous. But in fact, this is true for the exact wave function. So if your basis is large enough, then you will have the continuity of the derivative. But if the basis is not well adapted, and I will show you an example, the derivative of the wave function is not guaranteed. So these are two important tests of the R matrix. Okay, so this is the alpha phase shift for L equals 0. So here I don't really care about experiment. This is just a numerical example. I just want to compare the calculation in different conditions. So I will not show any experimental results here. So this is the energy, alpha plus alpha energy, so from 0 to 25 MeV. The channel radius is 10 Fermi. And you have different calculations corresponding to different basis sizes. And the exact, well, you hardly see it, is the dark blue curve which is superimposed here. So the exact calculation is somewhere here. And you can see that when you use many basis functions, 20, you don't see any difference with respect to the, compared to the exact solution. When you decrease the number of functions, with 10 functions, you start seeing a difference here. And with 9 basis functions, then you see that the R matrix result is strongly different from the reference calculation. And this is due to the fact that your basis functions are not enough to reproduce the internal behavior. So let's decrease the R matrix channel. So you see here the 7 Fermis. And again, well, you see here that 15 basis functions is perfect. And you see that with 10 functions, you perfectly reproduce the exact calculations, while here with 10 functions, you have a significant differences here. So when you reduce the channel radius, you can also decrease the number of basis functions. And this is nice because you can reduce the computer times. So you may say, let's still reduce the channel radius. And this is what we get with 4 Fermis. And as you can see here, when you increase the number of basis functions, so you have 6, 7, 10, 15, you never reproduce exactly the phase shift. And the reason of that is that 4 Fermis is too small. We have seen in the potential before that at 4 Fermis, the nuclear part is, of course, not negligible. So you are not in the conditions of the applicability of the air matrix. So from these numerical tests, we can say roughly that 10 Fermi is too large in the point of view of the computer times. There are too many basis functions. A equal 4 is too small. You cannot apply the air matrix. And there is a compromise. As always, there is a kind of compromise. And in that case, 7 Fermi is a good compromise. Okay, so here this is a very specific case because we know the exact results. So this is a textbook example, but in general, we don't know the exact results, of course. So we would like to test the calculation without having a reference calculation. And this can be done by looking at the wave function. So let me remind you this curve. So this is for A equals 7 Fermis. And I'm going to look at the wave function at 5 MeV for A equals 7. So 5 MeV is here. You have here the exact phase shift, and here the results for n equals 7. So we would like to have a test to check the reliability of the air matrix calculation here with n equals 7. And this can be done by using the wave function. So I'm going to show you the wave function at 5 MeV. So this is the wave function at 5 MeV with 15 basis functions. So you have here in pink the internal wave function going up to 7 MeV. And after that, you have the yellow wave, the yellow external wave function. And you can see that, well, they are equal to the exact. The exact solution is in blue. You hardly see it. And you can see here that the continuity is okay and the derivative also is okay. And this is consistent with the fact that we had a good phase shift for 15 basis states. And this can be understood when you are looking at the different basis states. So this ng here should be n. It's a typo here. So these are the Gaussians, the 15 Gaussians that we have introduced in the calculation. Okay, these are plotted here. There are 15 curves. And the channel radius is here at 7 Fermi. And you can see that many of them are almost 0. But you still have 4, 5 basis functions which are significantly different from 0. So there is some flexibility of the wave function to reproduce the internal part. So this is for 15. And now if you repeat the calculation for 7, this is more interesting. So you have here again the blue wave function, which is the exact, the pink is the internal, and the yellow the external. And you see, of course, they don't match the exact solution. And also, if you look at the matching point here, 7 Fermis, the wave function is continuous because this is imposed by the air matrix. But you can see that the derivative is not continuum. There is a strong crossing. And this is due to the fact that the basis is not large enough. If you look at the corresponding wave basis functions here, there are 7 curves here instead of 15. And if you look at 7 Fermis here, almost all basis functions are 0. So if you make a combination of 0, you always end up with 0. And this is why the matching here is not good enough. So this is how you can test your calculation and predict whether the phase shift will be reliable or not. And another example with signed functions. So this is a typical basis which was used in the literature because it's chosen in such a way that the derivative is 0 at the channel radius. So all basis functions, so this is a basis function with I equal 1, 2, 3, and for each of these basis functions, the derivative is 0. So here you don't have to use the block operator because this is a specific choice of the basis. And then if you use that, you end up with this curves for the phase shift. So the red curve is the exact phase shift, and as you can see, this is 10, 15, 25, 35. You have to use a very large number, and you never, in fact, you never get the exact solution. And this is just because this is not a good basis. It's not flexible enough. You always have zero derivative. And well, in our recent review paper, we have presented the Lagrange mesh functions, and I will show you in a moment for CDCC. So the Lagrange mesh is a kind of basis functions which is well adapted to this kind of calculation. So this was an example of non-resonant calculations. So now let me show the same thing for resonant calculation, and an example which I will consider several times in today and tomorrow is C12 plus proton. In C12 plus proton, you have L equals 0 resonance just above threshold here. So the compound nucleus is nitrogen 13, the proton threshold is here, so all energies are from this threshold. And there is this resonance with 0.42 MeV energy and 32 keV as a width. And here you can also use the potential model, and well, this potential reproduces the energy of the resonance. And if you plot, and again, if you plot this potential, you find that the nuclear part is negligible above 6, 7 Fermis. So you cannot expect the Herr matrix to be accurate below this value. And again, so I will not go into detail, just show you the result. So you have the phase shift as a function of energy here, and the channel radius is 7 Fermis, and you have different calculations here. So the exact is the dark blue curve with this Breit-Wigner behavior around the resonance. And you have 3 Herr matrix calculations with 10 basis functions, 8, so both are okay, and now 7 basis functions. And here you see that there is a rather important difference. And again, you can see that if you plot the wave functions, so if you plot the wave function corresponding to this situation, this is what you get. So the internal part here and the external part there, so you see that the matching here is very poor. So you confirm that the phase shift is not correct. And now if you use the same calculation with 10 basis functions, then you see the matching here is perfect, and the wave function corresponds to the exact. So you can see, you can test the calculation with this, this wave function. So even if you don't know the final result, just looking at these conditions, you can predict whether the calculation will be reliable or not. Okay, so that was the main applications of the Herr matrix for scattering states. So you have a combination of basis functions going to 0, and then in the external region you replace by oscillating Coulomb functions. But in some cases, we also need to pay attention to the long-range behavior for bound states. We know, for example, for exotic nuclei, the binding energy may be very low, so the long-range part of the wave function may be important, either from bound states. And in that case, you can also use the Herr matrix. So if you compare positive and negative energies, so this corresponds, this is the Coulomb equation for scattering states, and the solution of that are the Coulomb function f and g. And if you have negative energies, you have the same equation with the same potential. This corresponds to the Coulomb potential, but the sign here is different. Instead of plus k squared, you have minus k squared. And the solution of this equation are the Whittaker functions. There is W and M, but M diverges, so it should be disregarded. So the solution of this equation is the Whittaker function. And we know that the Coulomb function tend to sine and cosine functions, and the Whittaker function tend to an exponential. And so we can repeat exactly the same process as we did before, but just instead of having Coulomb functions as an external contribution, now the external contribution is this Whittaker function. And the coefficient in front of that, C, is called ANC, asymptotic normalization constant. So we discussed about that last Friday. And this C is important in external processes. So the coefficient here is exactly the ANC. So now, if you do exactly the same procedure as before, so you insert this expansion in the wave function, and then here you have to choose a specific constant for L. If you choose this constant as the logarithmic derivative, then the right-hand side of this equation is 0, because the block operator applied to this external part is 0. So this is a standard diagonalization problem. So you have this sum here equal to 0. This is a traditional diagonalization problem. So you can use any subroutine that you like to diagonalize. But there is one problem, is that here there is this function L, and this function, this constant L, the constant L depends on the energy, and you don't know the energy. So this is an iterative procedure. So you start by using L equals 0, then you diagonalize, you find an energy, then you introduce this energy in the new L, and you repeat the process until convergence. And this is applied here to the ground states of nitrogen-13. So you have here the ground state, which is bound by 1.94 MeV. And here the potential is slightly different. It should be less deep. This potential reproduces the binding energy here, and the basis functions are again Gaussians. So you can see here the result of the calculation for, well, the channel radius is 7, and there are 2 conditions for 6 and 10 basis functions. So these are the results of the iteration as for the different conditions, n equals 6 and n equals 10. And you can see here that n equals 6 converge, but to a wrong value, and n equals 10 converge after 3 or 4 iterations to 1.94. And again, you can, this is the same problem as before, n equals 6 is too small. And again, you can compute the left and right derivative just to look at the matching of the wave function. And here for n equals 6, the left and right derivative are, you see, they are very different. And for n equals 10, they are almost identical, so you are in the right condition. And again, you can plot the different wave functions. So this is n equals 6. Here 6 and 6 in a linear scale and in logarithmic scale. You see here very well in this logarithmic scale, the matching is here very poor. And here for 10 basis function is very good. So this confirms the previous results. Okay, so as I said, this is a textbook example, and you will do some exercise with that this afternoon. And well, if you like to understand the R matrix, I warmly recommend you to write a small code. To do that is 30 or 40 lines in Fortran. So if you want to understand how it works, these are very simple exercises. But of course, the R matrix is not essentially for that. This is for some applications where we don't have the solution, of course, and these applications are listed here, some of them at least. So microscopic cluster models, so it will not be for next week, but for the day after tomorrow. There are CDCC calculations, and I will show you some example right now, and also three-body continuum states. This can be done in hyperspherical formalism. And in each case, we end up with a set of coupled equations that we solve with the air matrix. So the principle is exactly the same. So let me finish my talk with some example on CDCC. So this will be on deuteron scattering on nickel. So I think you did this calculation with Fresco. So this is another example. And of course, we could use Fresco to test the calculation and to make sure that both are equivalent. So you know about CDCC. This is just a short reminder. You have a projectile which is made of two particles, and the Hamiltonian of the system is an internal Hamiltonian here, a relative kinetic energy corresponding to this term, and two potentials between the targets and constituent 1, constituent 2. So these are in general optical potential. And the CDCC has always two steps. The first one is to diagonalize H0, so you need a basis for the projectile, and expand the total wave function over this basis. And at the end, you have a set of coupled equations. So here it's deuteron plus nickel. So the first thing we should do is to diagonalize the deuteron basis. And here we use Lagrange functions. I will show you in a moment how it works. And you have here a bond state which correspond to the ground state of the deuteron, and all other states are called pseudostates, and they represent approximation of the continuum. So this is how you treat the continuum. You can also treat the continuum with bin functions. Probably you have heard about that last week, but I don't want to enter into detail. So what you have to do once you have this function is to introduce them in the expansion of the total wave function. So you have two coordinates, capital R and small r here. You have angular functions. These are well known. These are the two-body wave functions that you have found before. And these are the relative functions that you want to determine. So the first thing to do is to expand the potential. So these are known functions, in general, Woods-Saxon or Gaussian optical potential, and then you insert this expansion in the Schrödinger equation, and you end up again with this coupled system of equations. And the potentials here are simply determined from matrix element of the two-body states. So this is the common procedure for all CDCC calculations, determining the two-body states, the determination of the coupling potential, and then to solve this coupled channel system. And you know, one method is the one used by Fresco. It's a Numerov algorithm, and here I'm going to show you results with the air matrix. And here just one slide about the Lagrange mesh. This is a method which has been developed essentially by Daniel B. in Brussels. And the idea is to develop a basis, a set of basis functions, which can be used in any field, not only in nuclear physics, but only in atomic physics or particle physics. So a set of basis functions which is convenient to use for matrix element. So you know the Gauss approximation of an integral. And this is a numerical definition. You can approximate an integral by this Gauss type formula, where n is the order of the Gauss approximation, x chi are the rules of some orthogonal polynomial, and the lambdas here are the weights. And if you have a finite interval, you will use Legendre polynomials, and in infinite, you will use a Laguerre polynomial. So from that, you can define Lagrange functions, And here I take an interval 0 to 1 because it's just a scaling factor if you want to go to 0 to a. And these Lagrange functions are simply the Legendre polynomial divided by x minus the root of the Legendre polynomial. So these xi are the root. And now if you choose the coefficient here in such a way that you have this condition, then you can easily compute the matrix element. So let's take an example with the overlap. So the overlap of two functions is defined by the integral of these two functions. And now if you use the Gauss approximation here, you have a sum. It's simply use you simply use the Gauss approximation. You have a sum over k of this expression. And now with the Lagrange property, you easily find that this overlap is delta ij. So you don't have to compute the overlap. You know that at the Gauss approximation is 1 or 0. For the kinetic energy, here you have some analytical calculation to do, but you have to do once. So anytime you change the potential, the kinetic energy is, of course, the same. And the nice thing is for the potential, because if you look at the matrix element of the potential, so you simply write the exact definition of this matrix element. And again, if you use the Gauss approximation, then you end up with this very simple result. So there is no integral. You simply evaluate the potential at the root of the Lagrange function. So there is no integral which are needed. So these are very simple matrix elements. So this is why it's widely used now in many fields in nuclear and atomic physics. And this can be extended to non-local potentials. I don't show it, but it's very simple. So this was done with the student Thomas Druet. So we expanded here the deuteron functions in Lagrange basis, and then we compute the coupling potential, which are very simple to determine. And then, as usual, we determine the matrix, well, I called it D before, now it's matrix C. It's a generalization to multi-channel calculation. And because of the use of this Lagrange mesh method, the calculation of that is very fast. Then we have to invert this matrix and determine the R matrix, then the scattering matrix, and then the cross sections. So you have here typical conditions, about 30 to 40 channel basis functions, 100 channels. And again, you have to choose A as a compromise. So here it's a fast calculation, and there is no integral to determine the wave functions. And so a good advantage of that is that you determine the basis by the channel radius and the number of functions. So there is no further parameter. And well, one traditional basis is Gaussian functions. And in Gaussian functions, you know that you have to choose the width of these functions. And this is something difficult to optimize. But, well, there is a small technical problem, which is that Legendre functions have more zero at the borders of the interval. So we are trying to find still better Lagrange function, but this is not important. So the example I'm going to show you is a standard benchmark in the calculation, and probably this is what you have done as an exercise with Fresco, is deuteron plus nickel 58 at 80 MeV. So the Pn potential is a Gaussian, reproduce the binding energy, and we use standard optical potential for nucleon nickel. So the deuteron basis is shown here, and from this deuteron basis we determine the potentials. And these are the potentials, the different potentials that you will enter to the system, and this provides you some hints about the choice of the channel radius. If you look at the potential corresponding to the ground state here, it's shown here in blue. And you can see it's a short range. The range is about 5 Fermis, and it decreases very fast to 0. But if you look at another state, a pseudo-state, so this is the potential corresponding to this pseudo-state here, because this pseudo-state is extended as a long spatial extension, so this is shown in the potential. So the potential here goes to something like 15 Fermis. So it means that you have to choose the channel radius large enough to make sure that this potential is negligible. So here are the results. And first, something about the physics, and then I will come to the numerical aspects just after. So these are the experimental data, and this dashed line corresponds to the no breakup approximation, so just with the ground state of the deuteron, and probably this is something you have seen in the exercises. You cannot reproduce the data if you don't include the breakup, and when you include more and more partial waves for the deuteron and more pseudostates, then you can almost reproduce the data. And here are some air matrix aspects. So here the number of basis functions is 30, and you have 3 curves with 3 different radii. So you have 9, 12, and 15. And you can see that 12 and 15 are almost superimposed. There are tiny differences here, but you hardly see them. And 9 Fermis give these oscillations, and this is simply because of these pseudo-states. 9 Fermis is not large enough. Okay, so this is consistent with the potentials I've shown before. And here, the channel radius is fixed to 15, and I change the number of basis functions, 25, 30, 40. You see that 30 and 40 are almost identical, but 25 is different here. And again, this is as expected. 25 basis functions is not large enough to reproduce the internal variation. So, so here you see that 30 is a good choice. Okay, so let me finish with a technical aspect of the air matrix, which is called propagation. And this is something important when you have to deal with large systems. So the computer times is essentially made by 2 parts. One is the calculation of the matrix element. But as I told you before, with Lagrange mesh, this is very fast. There is no integral which is needed. So this is a minimal part of the calculation. And the main part, in fact, is the inversion of a complex matrix. So you may have very large matrices, 10,000 by 10,000. If this complex, this takes long computer times. And the problem is that in some cases you have a long range of the potential. And if you look at the Coulomb potential, this is written here. So capital R is the distance between target and projectile. Small r is the coordinate inside the projectile. And if you hide this expansion in multiples, you have the first term, which is the monopole term, which is, as usual, the usual Coulomb contribution. And then, at least when C equals C prime, you have one term which is 1 over R cubed. And QP here is the quadrupole moment of the pseudostates. And when you have very extended pseudostates, as this happens in this calculation, then this quadrupole moment can be very large. And then you have to go to very long distances to make sure that this term is negligible. And this is even stronger when you have dipole couplings. When you have couplings between 2 channels with angular momenta differing by 1, you may have dipole coupling, so you have here 1 over R square, not R cube. And then you may also have a very important contribution for large distances. So in that case, you have to use a large radius, so it means that you may have very large bases. And this is a problem because it's related to the inversion of the matrix C. And a solution of that has been proposed many years ago in atomic physics. So the idea is to propagate the air matrix. And I will finish with that, with the main idea of propagation. So if in the standard calculation, you have an interval from 0 to a, and you have n functions here. So what you need to do is to invert a matrix with a size given by the number of basis functions, n, times the number of channels. So the number of basis functions can be sometimes hundreds, and the number of channels 100 or 200. So this is a very large matrix. And the idea of the propagation is to avoid these large calculations by splitting your interval. So your interval 0 to a is split in some intervals. So I call here ns. And in each, because each interval is smaller, it's of course smaller than the initial interval, then you need less basis functions. So the idea is to compute the matrix element in each sub-intervals. So you have to repeat the calculation in each interval, but the inversion of the matrix is much faster. So from interval 1, you determine the air matrix here, and with interval 2, you can propagate the air matrix to A2 and then to A. So you replace one big calculations by several smaller calculations, and at the end you save a lot of computer times. And again, what you have to do is to compute matrix elements not from 0 to A, but from a finite distance to another finite distance. And again, the Lagrange functions are well adapted to this calculation. But this technique has been introduced in atomic physics to describe electron plus atoms, and you have the same problem with the long range of the potential. Okay, I think I'm done here. So tomorrow I will show you the phenomenological aspects and show you that it starts from the same origin as the calculable variant. Okay, it's time for coffee.